So we've covered a lot of ground in Unit 4. Let's take a few minutes now to sort of summarize and recap the important points that you should take away from this unit. We set out with some learning objectives. The first was to become familiar with the general current equation and what we mean by basic quantities like transmission, channels, Fermi window, ballistic transport, diffusive transport. Our second objective was to understand how current in a small nano device is related to the Fermi levels in the two contacts to that device, and how current in a large bulk semiconductor where the contacts aren't important is simply proportional to the gradient of the corresponding quasi-Fermi level. We wanted to understand drift velocity and be able to compute it, and we wanted to understand concepts like conductivity and resistivity. We also wanted to understand how the mobility is related to the microscopic semiconductor parameters, scattering times and effective mass, and how to compute the diffusion coefficient by using the Einstein relation. Putting that all together, we wanted to understand the drift-diffusion equation, how it relates to this more general current equation, and also what is meant by hot carrier or high field transport. Then we wanted to develop an understanding of some important carrier recombination mechanisms. These are important out of equilibrium, what we mean by low-level injection, how we determine the minority carrier lifetime when several processes are occurring. And finally, we wanted to understand carrier generation processes. Thermal generation, impact ionization in a high electric field, optical absorption in direct and indirect gap semiconductors. So let's quickly go through some of these concepts as you review what we've done in Unit 4. We began with this general current equation. Frequently, the approach that we've been using here is called the Landauer approach, after the scientist who first explored these ideas of the centrality of transmission to the understanding of current flow. We developed, or presented simply, a simple expression for the current. There were a number of fundamental constants out front. There was a quantity we call transmission, which is simply a number between 0 and 1, representing the probability that an electron injected from the first contact exits from the second, or vice versa. There was a quantity called the number of channels in which the current can flow. And there was a difference in Fermi levels between the two contacts, which we referred to as the Fermi window, the range of energies over which current flows. Well, let's look at some of those parameters. Transmission is directly related to how much scattering is in the device. And by scattering, we relate that to the mean free path, the average distance between scattering events. And we saw that there's a simple relation between the scattering length, the average distance between scattering events, and the length of the device itself. We looked at that in two limits. One limit we called the diffusive limit. The diffusive limit, and actually the diffusive limit can occur with an electric field too, but the diffusive limit simply means when the device is many, many mean free paths long and the transmission is very small. There is a corresponding ballistic limit for very short devices. For very short devices, devices that are short compared to a mean free path, the transmission can approach 1. So two important limits. In general, we're somewhere between those two limits. We also had this quantity m of E, the number of channels. And as we discussed, a channel is simply a state that has a velocity. It's a state that an electron can reside in, but the electron must be moving to carry current. So let's look at this simple EK relation for a 1D semiconductor. And let's ask ourselves, at the energy E, is there a channel? Well, if we look to the left or look to the right at the positive Ks, we can see that there's a state at that energy. Okay? We can see that that state has a velocity because velocity is proportional to the slope of dE dk. So it's a state with a velocity. There is a channel in this case. There's also another state with a velocity in the negative direction, but we only count the number of channels flowing in one direction. We know that there's an equal number in the opposite direction. So a channel is a state with a velocity. So this is all we really needed to know to understand how current flows in a very small device. So if we think of our small device characterized by some energy versus momentum or EK relation, and we have two contacts, one with a Fermi level 1 and the second with a Fermi level 2. In this case, it's lower because we've applied a positive voltage to contact 2 and pulled the Fermi level down. Current will flow. It's easiest to understand how current will flow at 0K, where all states below the Fermi level should be filled and all states above the Fermi level should be empty. So if we look below the Fermi level of contact 2, that's below the Fermi level of both contacts, so all of those states are filled. F1 minus F2 is 0. It contributes nothing to current flow. If we look above the Fermi level of EF1, all those states are empty, both for contact 1 and contact 2, so F1 minus F2 is 0. And again, they're irrelevant to current flow. The only states relevant to current flow lie between the two Fermi levels. Between the two Fermi levels, the probability that a state in contact 1 is occupied is 1. The probability for contact 2 is 0. So F1 minus F2 is non-zero. That's where the current flows. And this gives us a simple physical picture. So contact 1 sees that that state is empty. It should be filled because it's below the Fermi level of contact 1. So contact 1 sends in an electron to fill that state. Contact 2 looks at that state and says, that state is above my Fermi level. It should be empty. The electron flows out into contact 2 to empty the state. And this process completes itself continuously, and we end up with a current flow that goes, electrons come in from contact 1, fill the state, the electron goes out into contact 2, empties the state, and that gives us a current in the opposite direction entering contact 2. That's how current flows in a very small nano device. Difference in Fermi levels of the two contacts. Now, if we look a little more closely and ask what happens when we apply a small voltage difference, and we'd say we're near equilibrium now, we're going to assume that the temperature of both contacts is the same. Then we showed with just a little bit of math that F1 minus F2 is proportional to the voltage that we apply. And the constant of proportionality has to do with the derivative of this Fermi function. And we can see that minus that derivative is peaked near the Fermi energy. This is what we call the Fermi window. This is the range of energies that are important to us for understanding how the current flows. You can convince yourself easily that it is a few kT wide. If we call this function, this minus dF naught dE, a window function, W of E, then it's an interesting little problem to show that the area under this function is 1. As we cool the semiconductor down, it gets narrower and narrower in energy, so it becomes a delta function. So that's important to understand. We'll use it in a minute to try to simplify the mathematics of one of these problems. So in general, whether we're at 0K or whether we're at room temperature or whatever, because the Fermi window is proportional to voltage, current is proportional to voltage. We get current is conductance times voltage, and we have an expression for the conductance. This turns out to be a very general expression for the conductance of a material, a metal or a semiconductor or whatever. It's usually derived by much more advanced techniques, usually in a graduate course. We derived it with some very simple arguments here. So that's the general expression for the conductance of a slab of material. Let's look at small bias, where we have this approximation for the Fermi window. Then the conductance is given by this expression. Now let's look at t equals 0. At t equals 0, this derivative becomes a delta function, and it becomes easy to do the integral. We find that the conductance at very low temperatures is some fundamental constants, 2q squared over h, which has the units of, I think, 1 over, 12.9 kiloohms, times the transmission at the Fermi level, times the number of channels that there are at the Fermi energy. Well, that's an important result, something that people discovered in the late 1980s, early 1990s, when they began doing experiments on very small nano devices. This is a very small two-dimensional resistor. It's very short between the two contacts, so the transmission is close to 1. And the width of this resistor here can be controlled electrically by reversed bias Schottky barriers. If you measure the conductance of this little nano resistor, what you'll find is that as you make the resistor wider and wider, the conductance increases in discrete steps. Each time you add one more channel, and by making it wider, we can add channels one at a time, we get a discrete increase in conductance of 2q squared over h. So the fact that conductance is quantized is now a well-established experimental fact, and if we're working on very small devices, it's something that we have to be aware of and take account of. Now, most semiconductor device work is still done at a larger scale, where we can make use of current equations that apply in the bulk, where the number of channels is large, and we simply refer to the number per square centimeter. And we saw that in this case, we can develop an expression for the current, and we can write it in this way. Current is conductivity times the gradient of the quasi-Fermi energy divided by Q, the charge on an electron. Energy divided by coulombs has the units of volts, so we call this the quasi-Fermi potential. Current is proportional to the quasi-Fermi potential. The conductivity is a very important quantity. We can write it as the density of electrons times their charge times the mobility of the semiconductor. So we end up with this very important relation for the current flow in large devices or large bulk semiconductors. This is where the majority of semiconductor device work is still done. Let's take a look at that current expression. If we remember how the quasi-Fermi level is related to the electron density, we can then rewrite this equation. We saw how we can rewrite this equation as the sum of a drift part, drift in the electric field if it's present, and a diffusion part, diffusion down a concentration gradient if one is present. That's our drift-diffusion equation derived from the more general expression. And then the diffusion coefficient in this expression is obtained from the mobility through the Einstein relation. So it's important to understand drift current and diffusion current. Well, drift current comes from the fact that there is a drift velocity. Remember that electrons are zipping around in random thermal motion at about 10 to the 7th centimeters per second in a semiconductor, but superimposed upon that is a small average velocity given by the electric field if one is present. If we measure that average velocity versus electric field, we'll get characteristics that look like this. If we do that for silicon, we get a monotonic increase and then a saturation. If we do it for a 3,5 semiconductor like gallium arsenide, we get a much more interesting characteristic. And we discussed how this is related to the particular band structure of gallium arsenide. Now, if we look at small enough electric fields, we can see that the velocity is proportional to the electric field, and the constant of proportionality is the mobility, a very important parameter for semiconductor materials. If we go to very high electric fields, the high fields have accelerated carriers, electrons or holes, whatever they are, and given them lots of kinetic energy. If we measure that kinetic energy through a temperature and say it's equal to 3/2 kT, their temperature is very hot. So this is called high field or hot carrier transport. We can actually patch up our drift velocity expression if we appropriately define a field, an electric field dependent mobility. Now this gets a little bit into advanced transport theory. Oftentimes it works, sometimes it doesn't, but it is still widely used in semiconductor work. So let's take a look then at our drift current. We talked about drift velocity. Well, we expect the faster the carriers flow, the more the current is. So we have expressions for the hole and electron drift velocities. Drift currents, I'm sorry. And if we use our expressions for drift velocities, we have expressions for the drift currents. Notice that the sign is the same for both hole current and electron current. You should be sure that you understand why the sign is the same. Remember that the mobility is related to the microscopic material parameters of the semiconductor. And we also talked about resistivity and conductivity. Conductivity is NQ mu or PQ mu. Resistivity is 1 over conductivity. So we have a resistivity for electrons, we have a resistivity for holes. In an N-type semiconductor, the resistivity for electrons dominates. In a P-type material, the resistivity for holes dominates. In general, we'll have both electrons and holes. The total conductivity is the sum of the two conductivities. The total resistivity is 1 over the total conductivity. So resistivity, conductivity are important semiconductor parameters. So our drift diffusion equation had two terms, a drift term and a diffusion term. Let's recall the diffusion term very briefly. Let's say that we have two concentration profiles here. I'm showing one on the left for holes and the one on the right for electrons. Well, particles in random thermal motion will always diffuse down a concentration gradient. We talked a little bit about the physics of that process. So there will be a flux of holes down the concentration gradient, and there will be a flux of electrons down the concentration gradient. Well, holes carry their positive charge with them, so there will be a hole current in the positive x direction. Electrons carry their negative charge with them, so there will be an electron current in the opposite direction to the direction that the electrons are moving. So we have a hole diffusion current, and we have an electron diffusion current. In this case, they have different signs. So you should be sure you understand the difference in signs of these diffusion currents, why it is there. Well, that's our drift diffusion equation, which comes from the more general equations that relate current to gradients of quasi-Fermi energy. Total current, again, we simply add the two currents. Mobility is related to microscopic parameters. Diffusion coefficient is related to the mobility. These are some fundamental concepts. You want to be sure that you understand these are really the basis for all semiconductor, almost all semiconductor device work. Now, you might ask yourself, when are these equations valid? So let's just briefly say a thing or two about that. They're valid for large bulk semiconductors, many mean-free paths long, where the transmission is very small. They're also technically only valid near equilibrium, small enough electric fields or small enough concentration gradients, small gradients in the quasi-Fermi level. Although, as I mentioned, we can kind of patch these up for high fields by appropriately defining a electric field dependent mobility. That's something that needs to be done carefully, and there are cases in which it doesn't work. That requires a little bit of advanced transport theory that you would need a second course probably to understand more deeply. Okay, so we can make them work in cases, but be careful with using them. I also want to point out that we have assumed that there are no temperature gradients, that the temperature is uniform along the semiconductor. Temperature gradients can cause current to flow also. We would have to add something to our current equation proportional to the temperature gradient. Those can be important. They can be the basis of devices called thermoelectric devices. But in this course, we are not considering gradients in temperature. Okay, out of equilibrium, we have currents that flow. And we've talked about currents. You should be comfortable with those concepts. Out of equilibrium, we can also have carriers recombining. And remember, what we argued was that if we inject some excess electrons, small number of excess electrons into a p-type semiconductor, then we'll be in low-level injection. We haven't perturbed things very much. The semiconductor reacts by trying to bring things back to equilibrium. Those excess electrons will recombine exponentially in time, and the characteristic time is called the minority electron lifetime. There are various ways that the electrons can recombine, and we talked about three important ways. One is a direct transition from the conduction band to the valence band that emits light. That's called radiative recombination. Another is a process that's known as Auger recombination. Electrons from the conduction band recombine with holes in the valence band. The energy is given up not as light, but the energy is given to another electron or to another hole, depending on whether we're in an N-type material or P-type material. And the third is that defects can play a role in assisting these processes. So you want to have some familiarity with what those three processes mean. So let's talk about the first one, band-to-band or radiative, band-to-band radiative recombination. This dominates in direct gap semiconductors. An electron in the conduction band can recombine with a hole in the valence band. The energy can be given off as light. We can write the rate of change of electrons and holes. They're equal and opposite, right? What we're generating, where an electron is disappearing from the conduction band, a hole is disappearing from the valence band, so they have the same sign, they're equal. And we can write it this way. There's this B coefficient times NP minus NI squared. So we remember that in equilibrium, NP is equal to NI squared, so this is going to be 0 in equilibrium. What will happen is that there's actually an inverse process, and the two inverse processes cancel each other out, and we get no net recombination in equilibrium. What's Auger recombination? Well, an electron in the conduction band recombines with a hole in the valence band. The energy has to go somewhere. In this case, if it's an N-type electron, there are lots of electrons around. One of those electrons can accept that energy and be elevated to a higher energy state in the conduction band. So this would be an Auger recombination process in an N-type semiconductor. There's a simple expression. It's proportional one more time to electrons because we need an additional electron out front. We need one to recombine with a hole. We need another one to accept the energy of the process. And again, it is 0 in equilibrium. Now, there are also defect-assisted processes that can be very important. These are often referred to as Shockley-Reed-Hall processes after the three scientists who figured out how these processes work. So we have an electron in the conduction band, a hole in the valence band, but let's say we have some defect states in the middle of the band gap. These are states that are also frequently called traps. They can capture an electron from the conduction band and hold it there. So the electron is not free to carry current or move throughout the semiconductor, but it can occupy that localized state in the middle of the band gap. Well, then it can hop down a second time, and it can annihilate the hole in the valence band. This is a defect-assisted process. Where does the energy go? For processes like these, the energy goes into heat and heats up the silicon or semiconductor, whatever it is. Again, we can write an expression. This is a more complicated expression, and this time this is the expression that was worked out by Shockley, Reed, and Hall. But again, you can see that it's proportional to NP minus NI squared. So in equilibrium, the net recombination rate is 0 because there's an inverse process I'm not showing. So to summarize, if we take those expressions and if we simplify them for what's known as low-level injection, that means a small number of minority carriers in an oppositely doped semiconductor. So a small number of electrons in a moderately or heavily doped p-type semiconductor. Then we can simplify those expressions. And when we solve for the time dependence, we find that they decay, the excess carriers decay exponentially with time. And we define in this process 3 different lifetimes: a band-to-band radiative lifetime, an Auger minority carrier lifetime, and a Shockley-Reed-Hall or defect-assisted lifetime. In general, all of these processes will be going on at the same time, and they all shorten the lifetime of the electrons, excess minority carriers in the semiconductor. So the rates add up. The times don't add up, the rates add up, such that the net result is a shorter lifetime when multiple processes occur. Okay, just to summarize then, what you should take away is that the band-to-band radiative processes, these tend to dominate in direct gap semiconductors, and they form the basis, this type of recombination forms the basis for semiconductor lasers or light-emitting diodes. Auger recombination dominates when the carrier density is very high, and there's another carrier nearby to give the energy to. This can happen in a very heavily doped semiconductor. It can also happen in devices like semiconductor lasers, which can operate under very high densities of carriers when we forward bias them heavily. And finally, there's defect-assisted recombination. So in indirect gap semiconductors, where the direct band-to-band recombination process is weak, defect-assisted processes tend to dominate, or in direct gap semiconductors that have a high density of defects in them. Okay, so those are recombination processes. The inverse of each of those recombination processes is a generation process. So there's a thermal generation process, which is the inverse of Shockley-Reed-Hall recombination. There is an optical generation process that's the inverse of the radiative recombination process. Or we could also shine some external light, say the sunlight, on the semiconductor and have an optical generation that way. And then there's an impact ionization process, which in some sense is the inverse of the Auger process. But the Auger process can occur near equilibrium. The impact ionization process occurs when we apply very high electric fields and give carriers a lot of kinetic energy. So 3 important generation processes. If we look at the defect-assisted or thermal generation processes, we consider a semiconductor that has some defects in the forbidden gap. Now, instead of, remember what happens under recombination. If we have excess carriers, then an excess electron can be captured by one of these defects and then can hop down and annihilate the hole in the valence band, and that's a recombination process. And that will release thermal energy and heat up the silicon lattice. The opposite can happen. We can have a generation process where the recombination rate is negative. We have negative recombination, that's generation. What happens then is an electron from the valence band hops up and fills one of these trap states, these defect states, leaving a hole in the valence band. And then it hops up again into the conduction band, and now we have an electron in the conduction band. This takes thermal energy. And this is why this process is frequently referred to as a thermal generation process, the inverse of Shockley-Reed-Hall recombination. Now, optical processes, if we shine an external source of illumination on the semiconductor, we can create electron hole pairs. And if we have a high energy light, high energy photons, we can create electrons and holes with a lot of kinetic energy. They're far from their band edges. That's a measure of their kinetic energy. One thing I just want you to be sure that you remember is that that energy is shed very quickly. The electrons shed that energy by scattering from the lattice and giving the energy to the lattice primarily. And within a very short time, femtoseconds, that excess energy is shed and the carriers end up near the edges of the band. So in most cases, we've been saying the electrons in the conduction band are near the bottom of the conduction band. The holes in the valence band are near the top of the valence band. We can generate carriers with lots of excess energy, but we quickly dissipate that energy and the carriers end up near the band edges. That process is called thermalization. Okay, now let's look at this absorption process in a direct gap semiconductor. Remember that a direct gap semiconductor is one where if we plot energy versus K or energy versus momentum, crystal momentum, H bar K, that the maximum of the valence band occurs at the same location as the minimum of the conduction band. Now, if we shine light on a semiconductor like this, we can promote an electron from the valence band to the conduction band. The momentum does not change. They're at near K equals 0 or P equals 0 in both cases, which is good because a photon carries very little momentum. So momentum is conserved in this process. energy and momentum can both be conserved. This turns out to be a very strong process in direct gap semiconductors of this kind. Makes these materials very efficient at absorbing light and very efficient at emitting light under recombination processes. Now, you'll also recall that semiconductors like silicon are indirect gap semiconductors. In this case, an electron, the maximum of the valence band, occurs at a different momentum than the minimum of the conduction band. When we shine light, create an electron-hole pair, there has to be a change in momentum in order to satisfy both energy and momentum conservation. The photon doesn't carry much momentum. Where do we get the momentum needed? Well, that comes from a lattice vibration or a quantized lattice vibration known as a phonon. That's going to be less likely because we have to find a phonon with the right momentum in order to make this process work. So the optical absorption processes are weaker than they are in direct gap semiconductors. Indirect gap semiconductors are not efficient absorbers of light, and they're not very efficient at emitting light either. We don't build semiconductor lasers out of silicon, for example. Okay, we've covered a lot of ground in Unit 4. Just to remind you of some of these learning objectives, be familiar with the general current equation and key concepts like transmission, channels, Fermi window. Be sure you understand especially how current flows in the bulk and how it is related to the gradient of the quasi-Fermi level. Be able to compute the drift velocity when there is only an electric field present and understand what we mean by conductivity and mobility. You should understand how mobility is related to the microscopic parameters of the semiconductor and how the diffusion coefficient is related to the mobility. And you should have a good, solid understanding of the drift-diffusion equation. This is frequently the starting point when we sit down and analyze a semiconductor device. Well, non-zero current flow is one thing that can happen out of equilibrium. Recombination and generation are the other two. You should understand what those important recombination mechanisms are, and you should understand something about important generation mechanisms as well. Okay, we've covered a lot of ground in Unit 4. We've discussed some important concepts. Make sure that you take the time to be sure that you're comfortable with all of these important concepts. And then we're going to be ready to move on to Unit 5, when everything we've done in the course will come together and we'll put our basic understanding of semiconductor physics together in a way that we can use to understand the operation of virtually any semiconductor device. Thank you.